All right, so I don't know if you guys at home can hear that, but we hear that here at school. So here we go. I have an inclined plane, and the inclined plane has a box on it, like so. That does look like the Death Star. What's funny is people at home can see it. You guys just can't. I can fix that, maybe. And coefficient of static friction and mass of the box. So here we go. Here's the question. What is the maximum angle at which I can lift the incline and not have the box slide down the ramp? What is the maximum angle at which I can lift the incline and not have the box slide down the ramp? I believe you guys should have no difficulty in solving this problem, but let me point out, mu can be in your answer. All right. You can try m and g as well, but I think the entire answer can be based on mu. So take a moment, and when I say a moment, less than 3 minutes, see if you can walk through your set of steps and figure out the answer to this question. Oh, that's really going to be awful if I have to hear that every single time. But answer, theta equals inverse tangent of mu. But what should it should be equals. What should it be? Less than or equal to. That's right. You did it correctly. That's what you have. So tomorrow's quiz, at least this level. See nothing wrong with this. This one's easier than what we did on Friday. Raise your hand if you want me to walk through this one. All right, let's take a look at all the parts of it. Let's start with the free body diagram. And as free body diagram goes, I would think 3 forces. Downward force of weight, mg. I need a normal force perpendicular to the ramp. And I'd say friction up the ramp. Any question about those? As coordinate systems go, I'm thinking one aligned with the ramp makes the most sense. So I'll set up a coordinate system that's aligned with the ramp. Or at least try to. It looks like maybe I didn't draw that one perfect, so let's do a better job there. There we go. Now, I think we're going to take mg and break it up into 2 components. I think we'll have the component down into the ramp as mg cosine theta, and the component along the ramp, mg sine theta. No surprises there. Am I good to keep going? All right, so when I look at Newton's law, I'm going to use that the Newton's law is equal to 0. I don't want it to move. I don't know if you guys can see that at all. Probably should turn the lights out, but I don't want to stand up. So when I do that in the x direction, I'll get mg sine theta is equal to the frictional force. When I do that in the y direction, I'm going to get normal equals mg cosine theta. Any question about where any of that came from? Well, I'll remind you that our ultimate goal here is to demonstrate that the frictional force is where my inequality is. So when I'm going to look to find my threshold, plugging into the inequality is the way to go. So for normal force, I'm going to go there, and for friction, I'm going to go there. Now you guys put your hands up. If you're having trouble making it to the spot before this, you should ask where I came up with something. You sure, Sana?
I'm having trouble like remembering everything, but like I think I just need to like go through my notes and
All right. Had a little trouble hearing at the end, so maybe we're having some internet connection issues. But although this is something that you can memorize, it's not necessarily better for you to memorize. For a problem like this, certainly it'll make it faster. But the next one I'm about to give you, having it memorized like that might not help you. So I want to be very over the top
it
about
isn't
this.
that it's more so
You're fine. But I do think that there's a certain amount of practice that will help.
it wasn't that, it was more just what to plug it into. Like I think I may just be a little as far as internet connection goes.
Hey, we've all suffered it, Mr. Shelton among them. So hey, we just do what we got to do. Keep moving forward, right? When things happen like this, we just have a good laugh and move on. The substitution part is the part that brings us at least to a point where we might be able to find something out about the problem. But I do want to be very clear about it that I'm not doing anything here that we haven't already done. But at the same time, us plugging into the friction formula is kind of where we're going on this. But part of that's because we know where to go. We've done this problem before, or we've done something similar to this problem. So making those substitutions aren't unique or new. They're what we've been doing. When we get this mg sine theta, though, less than equal to mu mg cosine theta, we wanted the angle or something about the angle. But it should be clear that, I can cancel out everything about the size of the box here too. And once I've done that, it's not that it's obvious that it's done, but I do get, something where maybe I can make something happen here. You should be looking for opportunities to collect your terms when possible. And here's one of them. When I divide both sides by cosine, I get tan theta is less than or equal to mu. This shows up a lot with inclined planes. So being aware that this is here, that you're going to get this tangent function, it's not inappropriate. It's something that you should look at. So although I should go one step further and say theta has to be less than or equal to the inverse tangent of mu, I think basically the problem stopped when you recognize this. Questions? Go ahead. The rule on what? That's okay. I wasn't sure of your question, so I'm glad that they were able to answer it for you. But yes, tangent is a function. So you can take the tangent of both sides of an equation, and therefore the inverse tangent is also a function. You can take that on both sides of an equation. And the inverse tangent of tangent is just whatever the value is. It's like the square of the square root, All right, I was gonna ramp it up a notch, but I think I'm gonna keep it where it is. And this one is so simple. I think people screw it up because of that. Have you ever just hung something from your rearview mirror or seen it done? So you know that when you accelerate, it swings backwards towards you. So let's say that I have something I've hung on my rearview mirror and I accelerate so that it swings backwards. an amount equivalent to theta. So that the object itself, whatever that happens to be, let's say some knick-knack that I have on my, in my car. So there's my knick-knack. It has swung backwards, a distance theta. Knick-knack has mass m. I would like to know what the acceleration of the vehicle is in terms of theta. So that's the question. I'm noticing this thing swinging backwards. I'd like to know, what is the acceleration of the vehicle? M, theta, and g can be in your answer. Trust me when I say students make mistakes on this one a lot. You shouldn't. You guys are smart. Believe in you. I'd say like 3 minutes on this one. She's gonna yell. Sure as heck is. All right, you guys at home, you guys here in the classroom who are having troubles. I wasn't trying to be a jerk when I said there was only two forces acting in the system. I was trying to make sure you understood that this object only accelerates because it's connected to the car by the tension. So there's two forces that act on it. There's the downward force of gravity, mg, and then there's this force of tension. The force of tension should be drawn so that it's greater than the weight. This force of tension has to not only keep the object from falling down, but also has to apply a horizontal, unbalanced force that causes the object to accelerate. It's those two components that are working together. So I'm going to set up my coordinate system in the direction I think the car is probably accelerating, this way, the horizontal. And therefore, the vertical will be the part of the tension that's balanced by the weight. I'm going to set this as my angle, theta, because it's got to be the same as the angle here, because they are vertical angles. If I was to draw the horizontal there, I'm sorry, the vertical there, those two thetas would have to be the same because they're vertical angles. You guys remember that, right? Actually, these aren't vertical angles. These are alternate interior angles based on the old geometry stuff. Once I know that, it's not too hard to put together that I'm gonna have to break the tension into two components. There'll be this component and this component. Any question about why I've drawn it this way? I'm wrapping my triangle around my angle, which I've talked about before. This is going to be the cosine, and this is going to be the sine. Now, my net force in the x direction is not balanced. My system is accelerating in the x direction. But my net force in the y direction is balanced. That'll be 0. There's only one force in the x direction, and that's t sine theta. And that's got to equal ma. In the y direction, there's two forces. T cosine theta has to balance the weight. Any question where any of this has come from? Go ahead. How is this one theta? No. And I'll explain it again, but let me go to another page to explain it. So I'm going to draw a couple of lines. This white line represents a vertical line that is drawn to where the cable connects. Is that okay? So it's just a vertical line. It's where the object would hang if the car was not accelerating. But it's once we start to accelerate, the object on the end of the cable swings outwards, like so. And so my object is over here. Okay? Good so far? So I need to make my free body diagram line up with the mass of the object. So I'm going to draw in another vertical line to indicate my axes, or what will become my y-axes. Right there, okay? Now, would you agree that this line and this line are parallel? This is the angle that I was originally given. So by saying that those two lines are, that line A and line B are parallel to each other, and line C cuts between two parallel lines, by definition, the alternate interior angles have to be congruent. That's a geometric proof. Now, you might not like that proof. There's another way for me to prove it to you if you'd like. All right. So everybody else good? All right, so when I come back over here.
Could I ask that question? Sorry. Isn't the path taken an arc though, meaning that there would be like acceleration in both the x and y directions?
Which path are you talking about?
The path of the object as it like swings out.
See, you're talking about something that's not part of the problem. I agree with you that from the point when I start preparing for my acceleration to the point where I am accelerating, there will be the transitional period, but that's when the acceleration is changing. And I'm not asking about that. I'm asking about what the acceleration is that produces this particular angle. Okay. Your question is a little more complicated and one that's outside our scope here. Now, how you proceed from here is something I'd like you to pay very close attention to. There are tricks here that I think will benefit you in the future. And the first one is probably not to go about the way you would normally go when it comes to dealing with these two equations. I would assume that you guys would probably solve one for t and plug it into the other. But I'm going to suggest that you guys consider the idea that you can divide both sides of an equation by the same thing. I'm going to divide both sides of the equation by mg. But I know that mg equals t cosine theta. So on the right side of the equation, I'm dividing ma by mg and getting just a over g. On the left side of the equation, I'm dividing t sine theta by t cosine theta and getting just tan theta. Remember, you can divide both sides of an equation by the same thing, and we know that the same thing is mg and t cosine theta. They are equal. So I can divide both sides by what is essentially the same value, even though they're being represented by two different kind of algebraic quantities. It will save you a ton of time. Whenever you see something like this, t sine theta and t cosine theta, you might want to maneuver yourself so you can just do this kind of division. It's much faster. And when you do, you'll get that the acceleration is equal to g tan theta, which, by the way, is how you make an accelerometer. Go ahead. Yeah. I mean, how much time do we save by doing it this way? You know, quite a bit, I think. But also, it's a hope that you guys start to see some of that kind of pattern, that you can do that. You know, if I have two things that are equal to each other, I can use them on either side of an equation, you know, hopefully more efficiently. Does that make sense? I mean, if you don't like that, we don't lose anything by doing it the old way. Well, I think that's probably what most everybody does until they see this. I mean, the other way to do this is say, okay, t equals mg over cosine theta. And now I have this. I can plug it in there for t, and I get mg over cosine theta times sine theta equals ma. And of course, I get the same thing here. I'm going to get the m's to cancel, and I'll get sine theta over cosine theta. So g tan theta equals a. Same deal. Of course, the biggest thing here is knowing that you had to eliminate t. Some of you didn't know that. But t wasn't allowed in my answer. So the moment you realize that t isn't allowed in your answer, that's the thing to eliminate. A couple other points here, like I was trying to make. This is an accelerometer. All you need for an accelerometer is a protractor. You hang a small weight on a protractor and you can just mount it anywhere you want. It will tell you what the acceleration is. All you got to do is see how far back the object swings, and you've got a way of measuring something's acceleration. So they'll put these like on roller coaster rides and stuff like that for you to measure the acceleration. They generally don't do it so much on roller coasters because the thing bounces all over the place. So they'll usually use a spring and a tube instead, but this is an easy way to do it for two different directions. This one you can have it give you the positive acceleration and the negative acceleration. So a lot of the rides that go really fast in a straight line and then slam on the brakes, they'll do this. I like that one, okay. Easy, that could have been your quiz. You want another one? I got lots of practice. Lots of practice. Here's one, and I like this one because it will help all of those people who couldn't get the problem on Friday. Let's go back to an inclined plane problem because I love those. Not really, but you know. And I have a box on the inclined plane. Why not? There's always a box on an inclined plane. And these are getting pretty boring because they're all one body problems. And we're starting to run out of our one body problems. In this system, I can only apply a horizontal force to the box. A box that's parallel to the ground. The box has a massive M. The angle of the ramp is theta. There's a coefficient of static friction of mu s between the box and the surface. So this is the exact same question from Friday. What's the minimum and maximum force necessary to hold the box in place? This one has a more complex answer, and it's a more nuanced answer. Be careful with your angles here. This one, the angles can be deceiving. Would you guys like to work together on this one a little bit? I can break out these guys at home. You might want to have somebody help you look at your angles a little bit. So you guys at home, we're gonna do breakout rooms. Is that good for you? Or do you want one big room? I'll give you one big room. Okay, since the bell rings here in like just a minute, we do need to at least wrap this up a little bit. And I'm happy to work this out for you, but I don't think it'll work out in 1 minute. You've got both of these possibilities. You push too hard, friction's going to be down the ramp. You don't push hard enough, friction's going to be up the ramp. So this is really similar to the wall question, except that there's a ramp here instead. But your options are about the same. Now there is one kind of difference here, and that is it is possible that friction is big enough to keep the box in place without your force there at all. And your answer should be able to show you that. Because it's going to depend on things like the coefficient, the mass, g, these other things. So what I would encourage you to do is pick a direction for friction. We know this one's a possibility. You can push hard enough and it's just barely going to start to move. The issue is that you don't have a great direction to set up your coordinate system, and it doesn't matter. It doesn't matter if you set your coordinate system up to line up with the applied force and weight or the normal force and friction, because you're still only going to be able to line up two forces. So you're going to have to resolve the other two forces. That's what makes this problem hard. Give it a shot, though. See how you guys do. And I'll post a solution tonight on YouTube.